Hi, in this video we are going to see about undecidable and decidable language. So before talking about undecidable and decidable language, we'll just recall the search-Turing hypothesis. The search-Turing hypothesis states that a function of the natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. So what do we understand from the search-Turing hypothesis? So a function is solvable. A function on a natural number is solvable by a computer only if it is solvable by a Turing machine. So hence, the Turing machine is as powerful as that of our electronic computer. So, okay, so we have two types of problems. Generally, whatever problem we solve, so those problems can be divided into two types. One is decidable and another one is undecidable problem. So for both decidable and undecidable problems, Turing machine exists. But there is a major difference between the Turing machine that exists for decidable problem when compared to that of the Turing machine that we construct for the undecidable problems. Okay, so in case of decidable problem, the Turing machine always holds. That is, we know that for any mathematical model, the output is going to be either yes or no. So we'll construct a mathematical model, we'll pass a string to it. If a string can be accepted by the mathematical model, say Turing machine, then it says yes. If it could not be accepted, then it says no. So while saying yes or no, if it halts, then we say that the particular Turing machine or the particular problem is a decidable problem. So independent of the acceptance, the Turing machine halts. Whether it is going to accept the given input string or it may not be accepting the given input string, whatever case it may be, the Turing machine always halts. So in those types of problems, we call that as a decidable problem, right? So in case of decidable problem, the Turing machine produces the output yes and no. So if it can accept, it says yes. If it could not, it says no. But in case of undecidable problem, here also we have a Turing machine. But here the Turing machine does not halt always. It can halt only if it can accept the given input string. So it can produces only the output yes. So if it could not accept the particular given input string, then it will be an infinite loop. So it means it does not halt. So from the given diagram itself, we could be able to identify whether the given problem is decidable or an undecidable. Okay. So depending upon these two problems, the languages can be split into recursive and recursively enumerable languages. So when a Turing machine is a decidable one, then the language accepted by it is called as recursive language. If it is an undecidable, if a particular Turing machine is capable of solving an undecidable problem, then the constructed Turing machine is the language accepted by the constructed Turing machine is called as recursively enumerable language. So recursive in the sense that we have a Turing machine and that Turing machine is going to say yes or no. So depending upon the string which we are going to pass as the input. So when a language is recursively enumerable, here also we will have a Turing machine. But what is the major difference between recursive and recursively enumerable? Here the Turing machine is capable of saying only yes. If it could not accept the string, then the Turing machine will be an infinite loop. Okay, with this definitions in mind, we'll go to the properties of recursive and recursively enumerable languages. The first property is if L is recursive, then L bar is also recursive. I think you may be knowing what is L bar. L bar is nothing but complement of a particular language. So the theorem proof is very simple when we understand the concept of recursive. So we know that when a language is recursive, there is a Turing machine which says yes when it can accept the string, else if it says no, indicating that it could not accept the given input string. Okay, so we'll assume that M is a Turing machine which is capable of accepting the language L. Okay, since this Turing machine language is recursive, it can give me two outputs. What are they? One is accept and another one is reject. Okay, so now we are going to construct a Turing machine that is capable of recognizing L bar. L bar is nothing but complement of it. Okay, so when what is the complement of it? When this Turing machine, that is the Turing machine which is constructed for L, says yes, this complement is going to say as no. Similarly, if this machine, that is the machine M which we constructed for the language L, if it says no, then the machine that we are going to construct for L bar is going to say accept, that is yes. So this how will be. So anyhow, we are getting two outputs, say accept and reject. Hence we can conclude that the L bar is also recursive. So this proof purely depends upon the basic definitions of recursive. Okay. So now we are going to construct it. How we are going to construct a Turing machine? Then this Turing machine M, which we have constructed for the language L, when it accepts, it has to say reject. Similarly, when this Turing machine M says reject, the Turing machine that we have constructed for L bar says accept. Right? So hence the Turing machine which we are able to construct for L bar is capable of producing the output yes and no. Hence we can conclude that L bar is also recursive. So now we'll see the second property, if L and its complement are recursively enumerable. So we represent recursively enumerable as RE. Okay. Then L is recursive. So I am repeating it. If L and its complement are recursively enumerable, then L is recursive. So when I say L is recursive, then at last we have to conclude that we have got a Turing machine that is capable of saying yes and no. Okay, fine. So let M1 be the Turing machine that accepts the language L, which is nothing but what is the language of M1? It is recursively enumerable. So what does it mean? It can say only S. So it will have only one output. So instead of S, here we are using accept. That's it. And M2 be the Turing machine that is capable of recognizing the language L bar. What is the name of this language? The name of this language is also recursively enumerable. So hence it also produces only one output. Okay. So this is the language L and this is the complement of it. Okay, anyhow, when I pass a string to both of these Turing machine, if a language is accepted by this Turing machine, say M1, it says accept. While the other one will not be saying anything. If it does not say anything, then if it says accept, then it means that this Turing machine M2 will not be accepting it. So I can conclude that it is rejected. Similarly, if I pass a string which can be accepted by M2, which is nothing but the complement of this L, then it produces the output accept. That is, it says yes. When it says yes, then we can conclude that the other Turing machine is going to say no. Anyhow, it will not be producing, but since these are complement of each other, we can infer the result from it. So hence, with the help of these Turing machine, I can say yes or no depending upon the input string which is passed for these Turing machines. Since I am able to produce yes and no, I can conclude that L is recursive.